Hey, good morning, everyone. We really appreciate the opportunity to speak to you guys this morning. For those that you're out there, we appreciate you giving us the time and hope we provide some benefit. For those who don't know me, my name is Brad Fritz. I'm an agricultural engineer and the research leader of the Aerial Application Technology Research Group with USDA ARS here in College Station, Texas. This morning, talk to you a little bit about the effects of nozzles and solutions on droplet size and some of the things that you can do to influence those to meet your desired application parameters. Decades of research have shown that while there are many factors that play a role in determining how much drift occurs, there are really three major players that sort of rise to the top. Application or release height of the spray, the droplet size being applied, and the wind speed present at the time of application. Again, these should be fairly obvious. Application height, the higher the spray is released, the further it travels downwind while it settles before it actually settles out to the ground. Droplet size, larger droplets are going to settle faster than smaller droplets, meaning that smaller droplets are going to get carried further downwind before they settle out and reach the ground. Again, wind speed, obviously, higher wind speeds are going to carry these droplets much further downwind before they actually reach the ground as compared to lower wind speeds. So while all of those are considered, really deserve our attention, this morning we're going to focus on droplet size. Wind speed's something that you really can't control. You just have to adjust the timing of your application to. Application height you can very easily control, but it further impacts things like spray uniformity, effective swath width, overall applied rate, etc. So we're going to look at droplet size and some of the things that you as an applicator can work with to dial in your setups to really meet that requirement for a given application. Before we get too far into things, I want to highlight that much of the information and the numbers and the data that you'll see here come from a set of models that you can download right now for your own personal use. These models will give you that droplet size data for most of the nozzles that we use in the aerial industry. And these models cover airspeeds that relate to both fixed wing and rotary wing airspeeds. There's both an Excel version and a smartphone app. You can go to the website that's given here to find both of them. And if you're looking for the smartphone app, if you go to your app store and search aerial sprays, you should find it. So when you're trying to hit a specific droplet size, the first place always to start is proper nozzle selection. Your choice of nozzle has the single biggest impact on what's going to end up happening in terms of the droplet size you deliver. So let's look at nozzles and the role that they play. I know this is a very simple graphic and it's something that I know is very familiar to most of you, but I think it's worth just looking at the different types that we have to work with. Anywhere from these straight stream nozzles to flat fans of varying fan angle, hollow cone nozzles, what I call this anvil deflection type nozzle, where the spray is exiting an orifice and it hits a deflector that deflects it at some angle to basically make it spread into a fan and provide the breakup. These should all be very familiar with you. The models that I mentioned have data on all of these types other than the rotary atomizer. The rotary atomizers is something that most of the manufacturers of the rotary atomizers have their own models, as these things depend on the blade angle, the fan screen size, a bunch of different parameters. So if you're using rotary atomizers, work with the manufacturer to make sure that those are dialed into what you want them to do. So let's look at the impact that just changing nozzle has on droplet size. To keep this fairly simple, we're going to keep all of the nozzles using a number 12 orifice, all operating at 40 psi, and we're going to look at two different airspeeds, one for fixed wing at 140 psi or 140 miles per hour, and one for rotary wing at 80 miles per hour. So with the fixed wing, as we decrease our fan, moving from an 80 to a 40 to a 20 down to a straight stream, we see our VMD, our volume median diameter, increasing quite a bit from 264 microns up to 435. Correspondingly, we see our percent fines decreased. In this case, we're going from 7.7% down to about 3.1% fines. Again, same trend with the rotary. at the 80 mile an hour. As we go from the 80 to the 40 to the 20 to the straight stream, we see VMDs increasing from 410 to almost 3 times that, over 1200 microns. And again, our percent fines correspondingly dropping from 1.7% to less than 0.2%. So again, nozzle selection has a very, very significant impact on what your final droplet size is going to be. So airspeed plays probably the next biggest role in the droplet size being produced. As the liquid exits the nozzle, it has some velocity that's tied to the spray pressure that's being used. That liquid then is entering into an airstream that has a velocity that's equal to your flight speed. The difference in the velocity between the liquid and the surrounding airstream is what drives the amount of secondary breakup that occurs. Just as an example, and shown here on the screen, if we look at typical spray pressures ranging from 30 to 60 psi, these are tied to nozzle exit velocities that are around 30 to 60 miles an hour. And with typical flight speeds ranging from, say, 120 to 160 mile an hour, we see differences between the liquid entering the airstream and the airstream itself of around 60 to 130 mile an hour. So the higher and the greater that difference in the velocities are, the greater the breakup and the smaller the overall droplet size being created. So what are some real numbers associated with this? If we look at airspeed's effects, we're going to look at here a 40-degree flat fan, number 12 nozzle, 40 psi. As we increase our airspeed from 50 to 160 mile an hour, our VMD drops to almost 50%, from 597 down to 275 microns. And our percent fines increase quite a bit more than that. We increase from about 0.5% to just a little shy of 7%. So again, airspeed has a huge effect on what's going on with droplet size. So let's look at the impacts of spray pressure. We're going to look at a 40-degree flat fan with a number 12 orifice. For a fixed-wing aircraft operating at 140 miles an hour, as we increase spray pressure from 30 to 60 psi, we see our VMD increase from 324 to 346 microns. Correspondingly, it's not shown here, but our percent fines decrease from 3.9 to 3.2%. This is contradictory to what you probably see on pesticide labels, as there's just sort of a misunderstanding with the product manufacturers on this, but just something to be aware of as you're going through your setups. With the rotary wing droplet sizes, they're potentially a little more tricky, as the lower flight speeds that we're operating at are right at that threshold where spray pressure and airspeed combination really has a significant impact relative to the secondary breakup that we talked about. So for the same 40-12 nozzle at 80 miles an hour, we see a slight increase in our VMD from 30 to 40 psi, going from 524 to 537, and then a constant decrease in VMD as we increase our pressure further to 60 psi. We see it going down from 537 to 511. Likewise, for the 50 mile an hour airspeed, we see a constant decrease in VMD from 30 to 60 psi, with our VMD reducing from 607 down to 534. These trends for both the fixed wing and rotary wing can vary by nozzle type, the orifice size, and particularly if you're using any sort of deflection angle. So the best way to confirm these is to dig into those models that we talked about and just work through your combinations of nozzle operation setup, pressure, airspeed, and make sure that it's getting the droplet size that you want for you. Orifice size is fairly straightforward. In this case, if we look at, again, same thing, we're going to look at a 40-degree flat fan for the fixed wing. As we increase orifice size from 0.6 to a 25, we see our VMD increasing from 300 to 371. Our fines correspondingly decrease from 5.8 to 4.1%. If we look at the rotary wing, in this case, I'm going to look at an 80-degree. As we increase over the same orifice size range, we're increasing VMDs from 316 to 536. Again, with our fines decreasing from 4.2 to less than 0.1%. Straight streams are a little bit different animal. If we look at the fixed wing, as we increase our orifice size from an 0.6 to a 25, we can see our VMD actually decreasing from 466 to 387. Correspondingly, our fines are going to increase from 2.4 to 4.7%. With the rotary wing, we see kind of what we see in the pressure. We have an increase and then a little bit of a decrease over that same range, with the fines doing sort of the same thing. So again, this is something where you would want to go to the models and confirm your setup, and see what your setup's doing in terms of actual droplet size. So now that we've covered, I guess, quote unquote, the easy stuff related to nozzle selection, again, these models should help you with that. Let's look at some general trends with respect to spray solution on droplet size. So first and foremost, and this shouldn't surprise anyone, anything that you add to water is going to change the overall physical properties. Again, I'm thinking surface tension, viscosity, which in turn changes the droplet size that results. So in this case, I'm looking at just a pure water spray. We have a VMD of, say, 352 microns. If we add something to this, and in this case, we added a non-onyx surfactant, we see a very significant decrease in the VMD from 352 to 288. So again, water alone is not something that we normally deal with in terms of a real world application. Realizing that the models that I mentioned all use water plus 10% non-ionic surfactant, which we have found is pretty close to the majority of the real world solutions that we spray. So, when you use those models, you should be able to feel a little bit of confidence that you're going to at least be in the ballpark of what your actual tank mix is doing. Adjuvant effects become a little bit more confusing as we throw more into the mix. This gets also hard because the data becomes quite large and quite difficult to visualize and explain. It's very tempting to throw up some plots and graphs and figures. Instead, I'm going to try to do sort of a Reader's Digest condensed version and try to do it a little more visually. So a study that we did here recently, we looked at a bunch of different solutions with PowerMax as the active ingredient for no other reason than it was a fairly high formulated product, and as a herbicide, it's one that we're concerned about in terms of risk. And then we looked at 6 different adjuvant types, ranging from crop oil concentrate, microemulsion, methylated seed oil, a silicone surfactant, and 2 different polymers. And I put these lettered combinations here, that's what on this next slide I'm going to show. These little squares are going to have the VMD from a solution, the percent fines for a solution. All of these PowerMax will all have this PM, and then otherwise, the letter combination in this bottom right-hand corner will reflect what solution was being used. So again, with we looked at here a 40-degree flat fan with an 0.8 nozzle, a 40 psi, 140 mile an hour. As we change these solutions, if we look at the PowerMax alone, we're at about 232 VMD, 11.5% fines. Basically, all the other adjuvants that were added to that solution either moderately or quite a bit increased the VMD. We see VMDs ranging from 239 for the silicone up to 268 for one of the polymers. However, not all of them decreased the percent fines. The crop oil concentrate, the microemulsion, and the methylated seed oil all decreased the percent fines to about 60% of what the PowerMax alone was. The silicones and the 2 polymers decreased or didn't change the percent fines all that much. These thickening agents just behave a little bit different. Again, this is just reflective of these 6 different adjuvants that we ran. But this is sort of the trend that we've seen with the data that we've run in the past. Solution effect by airspeed. So I challenged myself from the beginning on this not to have any graphs. But the next point just was so much easier to make with the graph, and you'll see why. Plus, I figured it'll make Scott happy to have a couple of graphs to that. So if we look at VMD for the same 7 solutions, and again, kind of returning a little bit to our discussion of airspeed, you can sort of see in this graph very quickly that at the lower airspeeds, the lines for the different solutions are farther apart. As we start getting to airspeeds of 130 to 140 and above, we really start seeing the lines that are reflective of the VMDs of the different solutions start coming together. And this is due to this secondary breakup becoming so much more significant in the overall process, and actually starts becoming basically the most dominant factor that's driving the atomization. meaning that as your airspeeds start increasing over 130, 140 mile an hour, your solution effect really lessens. With the percent fines, we see very similar trends. We can see a little more separation at the higher airspeeds, but again, as we start hitting particularly 150, 160, we really see these solution numbers really start to come together and just not have the separation in solutions. So again, just something to keep in mind is that the higher airspeeds, if you're depending on solution to give you a bunch of benefit in terms of your droplet size, you might want to revisit your nozzle setup. So with all of that information to try to digest, and a quick disclaimer that the takeaways, you really need to look at the models and verify some of these, but I kind of want to give you just some quick rules of thumb. First and foremost, always start with proper nozzle selection. This really gets you most of the way there to your desired droplet size. Wider angle fans are going to give you smaller droplet sizes as compared to narrower angle fans and straight streams. With respect to airspeed, you can anticipate about a 3 to 4 micron decrease in your VMD and about a 0.2% increase in your fines with every 1 mile an hour increase in your airspeed. On pressure, similarly, you can anticipate about a 1.2 micron increase in VMD and about a 0.1% decrease in fines with every 1 psi in pressure. On adjuvants, most of them that you add to your tank will improve the overall VMD. We've seen oils and emulsions have the potential to reduce your fines. Some of the thickeners may actually increase your fines. And then once your airspeed hits 130 to 140 mile an hour, your solution effect really diminishes. I really appreciate everyone's time this morning. I'd encourage you to visit our website for more information, for our contact information, and links to some of these resources. Anyone that has any comments, questions, or suggestions for additional research, please feel free to give me a contact at any time. Thanks again, and I'll be happy to try to answer any questions.